All right, so welcome to session 9.4. I'm hoping we can get this done in one video. All right, the idea of section 9.4 is to use the normal curve that we were talking about in 9.3 as an approximation tool for those binomial problems that we were working on back in chapter 8. All right, so our objectives are to how to determine when you can, how to find the correction continuity, and then use it. Okay, so binomial problems. All right, so some history. This concept, this idea of using a normal approximation for a binomial used to be really important. And then technology came along and took away the word really and made it just kind of important. And then more technology came along and took away the word important and just made it kind of useful, but not really important like it used to be, because technology has made it so we don't need an approximation technique for binomials because I can calculate them directly. Now, there are still applications in statistics, specifically when it comes to things called confidence intervals and also with respect to hypothesis testing. And you'll do that in your statistics course when you get there. But this is the math that's hiding behind what they do there. Okay? All right, so first off, I can only use a normal approximation technique for a binomial if the binomial fits the requirements. That is, the binomial is big enough. What I mean by big enough here is this idea of n times p and n times 1 minus p, both being greater or equal to 5. Now, I know what you're thinking. What the heck are n and p? So just to review really quickly, n was the number of trials of your binomial, and p was the probability of success. So then 1 minus p was the probability of failure. So this idea of n times p being greater or equal to 5 and n times failure, n times success and n times failure both being greater or equal to 5 is basically just simply saying that, hey, if you knock on enough doors, if you run enough trials of the experiment, you can approximate it using a binomial distribution. And if you can do that, then the mean of that normal distribution will be n times p, and the standard deviation of that normal distribution will be n times p times 1 minus p under a root. Okay? Here's what's happening in the mathematics. Let's assume that we have some sort of a binomial scenario where the probability of success is 0.25. If I only have a few trials of this experiment, the probability distribution here, this probability, remember this is a probability histogram, looks nothing like a normal curve. And n times p and n times q, I have a hard time with this. Most textbooks call that q, call failure q. I don't know why this one doesn't. I really dislike it because it would be so much cleaner. We could just simply say then the standard deviation is the square root of n, p, q. But failure here is q, success is p. And the n times the p and the n times the q here, the n times success and n times failure are both nowhere near 5. And our distribution doesn't look like a normal curve. But if I increase the number of trials of the experiment from 4 to 10, now my distribution is starting to look a little more curvy. It's not perfect yet, and the numbers bear that out. I don't have my 5s I'm looking for yet, but it's starting to look more like that. If I increase it to 25, now my numbers bear it out, and my graph does too. This looks like it's a pretty good normal curve there. And so I could model that reasonably well normal. And if I keep going and get bigger, it just gets bigger and better. So the more I do, the more n's I have trials of my experiment, the better my curve can be approximated by a normal distribution. Right? So here I have two binomial experiments. My job is to determine whether I can or cannot use a normal distribution to approximate these. So just some review to remind us what binomials look like. I'll start with the first one here. Okay. In a survey of 8 to 18-year-old heavy media users in the United States, 47% said they get fair to poor grades C or below. All right, so this just defined what we're calling success. Success is they get bad grades. I have a P of 0.47, which means my 1 minus P, my failure, is 0.53. Okay. You randomly select 45 8 to 18-year-old media users and ask them whether they get fair to poor grades. So that 45 now is my N. Because I'm knocking on 45 doors, I'm running 45 trials of this experiment. So could I use a normal distribution to approximate probabilities for this? Okay. Well, I'm going to check and see. My job is to do this only if I have enough. So is 0.47 times 45 bigger than 5? Yep. And is 0.53 times 45 bigger than 5? Yep. And I just did twice as much work as I should have done. Because here's the trick. Which of these is smaller? Only check that one. Because all you need to do is check the smaller one. And it doesn't matter whether the smaller is success or failure. But if the smaller one works, meaning if it gives you something 5 or more, then the bigger one will too. And so it's not a problem. So that means that for this scenario, I could answer probability questions by using my normal approximation technique. I know you don't know what it is yet, and that's fine, right? All right, let's take a look at the second scenario. In a survey of 8 to 18-year-old light media, it's not heavy, but light media users, 23% said they get fair to poor grades. All right, so there we defined our success to be poor grades again, but now we're at 23%, which means that our failure, 1 minus P, is going to be what, 77%? No. Yeah, 77%. 7, 8, 9, yeah. You randomly select, ooh, I'm only 20. Okay, so I'm worried now. My sample size is small, so I'm worried. All right, I normally am required to check, or I'm told to check both N times P and N times 1 minus P, but I'm not going to. I'm only going to check N times P because it's the smaller one. And if the smaller one works, the bigger one will work too. So I'm going to go ahead and grab my calculator. What is 20 times 0.23? 4.6. That's not big enough. So I can't use a normal approximation. So this one was yes. This one's no. I can't use a normal. Okay? All right, so let's look at actually using a normal curve approximation and see what that looks like. All right. There is one small issue that we have to deal with. A binomial distribution is a discrete model, and a normal is a continuous model. So what we have to do is we have to do something called the correction for continuity, or the continuity correction. Again, it just depends on who wrote the textbook. Okay? When you're calculating exact binomials, you would just have that x is equal to a single value c. But I need to turn that into an interval to make it work for my curve. I can't just have a number, I need an interval. I need a lower limit and an upper limit. So the way that I do that is I add and subtract 0.5 from both edges and turn a single value into an interval. Now I know you're looking at me going, wait, what? What is he saying? Well, suppose, and I don't know what these numbers are, but let's just make some numbers up. Suppose that this C right here was a 5. So that means that's 5. Okay. When I use the normal approximation, I turn that into an interval by taking that 5 and going down by a half and up by a half. So my interval is now 4.5 to 5.5. And that gives me a range of values. I need ranges of values to do my normal approximation. So the continuity correction turns a single value into a range. Now, what if it was 2 values? So what if it was this bar and this bar? Okay, let's check and see real quick. So if that was 5, that'd be 4, 3, 2, and 1. So this is 1, and this is 2. So then half down from 1 would be 0.5. Half up from 2 would be 2.5. So then my range would be, or my probability would be 0.5 is less than x is less than 2.5. So I take my lowest value and go down by 1/2. I take my highest value and go up by 1/2. And that turns my values, my discrete variable, into a continuous random variable. All right. If you're one of those people who needs some sort of table, here's a table for those values and what they would look like when you turn them into a normal. So these were the binomial words. These are the normal approximation adjustments. Okay? All right, let's take a look at an example. Let's actually work it out from start to finish. Here we go. In a survey of 8 to 18-year-old heavy media users in the United States, 47% say they get poor grades. You randomly select 45, so I've got a P, I've got an N. I know that my p-value, my probability of success is 0.47. That means that my probability of failure was 0.53. I know that I have a N of 45. I already checked this problem earlier, so I know I can do a normal approximation. So let's look for the question. What is the probability that fewer than 20 of them respond yes? Right? So binomial, I would want the probability that x is less than or equal to 19, because fewer than 20, discrete, random variable, next number down from 20 is 19, right? But I want to turn this into a normal approximation. So when I turn this into a normal approximation, I need to convert all this binomial junk over here into the normal junk. Well, the normal junk says you need 4 things. You need to know a mean, you need to know a standard deviation, you need to have a lower limit, and you need to have an upper limit, because those were the 4 values we needed, right? Well, I've got formulas for means and standard deviations. My mean was always n times p, so in this case that's going to be 45, because that was n, times 0.47, because that was p. And I got a formula for the standard deviation. It was the square root of n times p times 1 minus p. So that's going to be the square root of 45 times 0.47 times 0.53. 1 minus p. I got an upper limit, right? Because that's an upper limit. That's the biggest number, 19. So my upper limit is going to be 19.5. And where'd that 0.5 come from? Continuity correction that we just talked about. So that 19 turns into 19.5. I don't have a lower limit, but that's okay, because I've done lots of problems with normals where I didn't have a lower limit or an upper limit. I'm just going to use a negative big number to make it work. And then I'm going to bring up my calculator and I'm going to go ahead and put all this information in. I'm going to go to my distribution menu, a normal CDF. My lower limit is a negative big number. My upper limit is 19.5. My mean is 45 times 0.47. Yes, I am that lazy that I didn't even figure out what that number is, because honestly, I don't care. And my standard deviation, again, square root 45 times 0.47 times 0.53, close the parentheses. Again, I don't even care what that number is. I'm just going to plug it in, grind it out, press paste, press enter, and I get that that has a probability of 31%. So the probability that less than 19 or less than 20 people, that 19 or fewer people will say yes, they get poor grades, is about 31%. Right? Now, since this is a left tail binomial, right, I could have calculated this directly by going to the distribution menu and doing that binomial CDF, where I have 45 trials and a 43% chance of success, and I want that to be at most 19. And it could, oh, 47% chance of success. I've typed in 43. And I get 0.312. The approximation is 0.311, 0.312. We're off by 1,000th. Now, since I have the technology to do it directly, it seems kind of silly to approximate it. But if you think back to when we didn't have calculators, back in the day, okay, if you wanted to answer this problem, you'd have to do this. To do less than 19, you'd have to find the probability that x equals 0, plus the probability that x equals 1, plus the probability that x equals 2, and so on, all the way up to the probability that x equals 19. And you'd have to do every single one of these things by hand because you didn't have a calculator. Now, yeah, you could do that, but that's a lot of work. So this ability to approximate really quickly, even if I had to do this by hand and look up all of this junk in those tables like we did for that first example, that would still be a lot less work than doing any of this over here. So while we don't use this as much as we used to, this was a tremendous time saver. Okay? It was something huge that we used to do. I'm not going to do this one. I'm going to skip this one, but I am going to do this one right here. We'll take a look at one more example, then we're going to call it good. We're going to finish this in one sitting. All right. A study on aggressive driving found that 47% of drivers say they have yelled at another driver. You randomly select 200 drivers in the United States and ask them whether they have yelled at another driver. What is the probability that at least 100 drivers will say yes, they have yelled at another driver? Okay. That defines success. So success is we yell at somebody. Okay, but I have a probability of success of 0.47. I have a probability of failure, 1 minus p, of 0.53. Okay, wait a second, is this the same? Huh, that's interesting. Okay, I have an n of 200, and they want me to find that at least 100 will say yes. So the probability that x is greater than or equal to 100. And that right there, that's binomial. And I could calculate it directly, but they want us to approximate this using a normal. So in order to use a normal, I need those four things. I need that mean. I need a standard deviation. We'll put it up here because I ran a space down there. I need a lower limit, and I need an upper limit. Okay. My mean is always n times p. So that's going to be 0.47 times 200. Okay, now I'm hoping that at least one person caught it. I never checked that 5 thing to make sure that this was big enough. But I'm just going to be honest with you. I saw that 200 right there, and I did check it. I just said, well, that's like half. Half of 200 is like 100. This is going to be way big enough. Okay, so I technically didn't write it out, but I did check it. Okay. My standard deviation is the square root of n times p times 1 minus p. So that's going to be the square root of 200 times 0.47 times 0.53. Ooh, that's a lower limit, isn't it? So then my lower limit is going to be 99.5. Where'd that 99.5, where did that come from? Well, this is a bottom of 100, but I always have to take the bottoms down and the tops up by a half because of that continuity correction business. So a half a unit down from 100 is 99.5, and I don't have an upper limit, so I'm just going to use a stupid big number for that. All right, so I'm going to grab my calculator. Where's my calculator? My thing is frozen up. I'm going to pause. Oh, please, please, please come back. Oh, it's stuck. I hope it's recording. Is it recording? Is this working? Oh, please tell me you didn't break. Oh no. Oh, I don't know, there it's working. Let's see, this is going to be, let's see, second distributions, normal CDF, lower limit is 99.5, upper limit is a big number. My mean is 0.47 times 200. Oops, I lost my 4. 47 times 200. My standard deviation is 0.47 times 200 times 0.53. Close my parentheses, paste that back in. I get a value of 0.217. And so it looks like we have a probability of about 22%. So there's a 22% chance that 100 people or more will say they have yelled at another driver. All right, that brings the next section 9.4 to a close. I'm going to end this video and I'll see y'all back here for what? Chapter 18 after this one.